We've started talking about electricity and magnetism. We haven't done any calculations yet. Anyone have any questions about just the overall stuff I brought up, the kind of overview? All right, so basically, electricity and magnetism is going to kind of follow this rough outline. So there are two parts. The first one is how current produces magnetic fields. And the second one is how magnetic fields produce current. And we're doing this one right now. All of this electricity and magnetism, and especially this first part, calculating the magnetic fields produced by currents, are going to depend heavily on this this relationship between directions called the right-hand rule. So the trickiest thing, now we're talking about current producing magnetic fields. We're going to be calculating the produced magnetic field vectors those are going to be always called the B vectors. And the B vector is going to be broken up into a magnitude and the magnitude is going to come from something called Ampere's law. For the most part, this is going to be the easy part. And a direction. The direction is going to come from three different applications of the right-hand rule. And actually, change that to two. The third one isn't really exactly the same thing. But so two different applications of the right-hand rule. And this is the tricky part. If you can make sense out of this, you're not going to have any trouble with this topic. Some people find this pretty natural, and some people struggle with this. So today I'm basically going to be talking about the right-hand rule and how it applies to the magnetic fields produced by current. Okay, so the trickiest part is dealing with directions. And since we're going to be dealing with directions that are in different planes, so we'll be talking about the relationship between a rotation that sort of follows one plane and a vector that points in a direction out of that plane. I'm going to have to be representing vectors that not just point up and down and side to side, but also point in and out of the board. So I know this came up briefly when we were talking about circular motion, but I just want to remind you, so that would have been last semester, just remember that if you see a symbol like this, that is a vector. What direction is that vector pointing? What? That's out of the board, yep. And then one that's going into the board is an X. So just think of it as an arrow. This is the point coming towards you, and this is the feathers leaving you. All right, and now the right-hand rule. The right-hand rule is a relationship between a rotation direction and a vector direction that's perpendicular to the rotation. Okay, so so if that disk represents a rotation direction, the right-hand rule gives you a relationship between the direction of rotation on this disk and an arrow pointing out of the disk. The disk is the rotation. The arrow is the perpendicular vector. And so the right-hand rule, I mean, I think part of the difficulty, maybe most of the difficulty, is just being able to think in 3 dimensions the way you have to do these problems. Part of it, though, is that this thing here is what your right hand is really trying to simulate with the right-hand rule. And your hand has a lot of annoying properties that this doesn't. You know, your hand has other, like, good qualities that this wouldn't, you know, like whittling, you know, you couldn't whittle with this thing. But on the downside, so this is how the right-hand rule represents this shape. A weird thumb you have. Okay, so there's your hand. So your thumb represents the vector, and the way your fingers curl represent the direction of the rotation. Okay? But you have to remember to have your thumb be perpendicular to the circles that your fingers are representing. So, like, I've seen a lot of people get things wrong because they hold their hand like this and then their thumb's pointing in the plane of that rotation. You know, I've seen a lot of people make the mistake of using their left hand for the right-hand rule. But actually, so notice that the relationship between, you know, the vector and the rotation direction is opposite on your left hand. And so, like, on tests, I see a lot of people, since they're writing with their right hand, to save time, they don't put down the pencil and do it with the left hand, and then you get your directions all backwards. Somebody told me they use the left-hand rule instead and tuck their thumb in under the, I'm just like, come on, really, why? Don't even, if you're going to do that, fine. But just don't tell me about it. That works fine, though. And the right-hand rule comes up in, so the fingers curl in the direction of the rotation. And the thumb is the perpendicular vector. And it turns out, I mean, like, how often would you need to have a relationship between a rotation and a perpendicular vector? It turns out all the time in physics and math. It comes up a ton. So it's super important in physics and math. Here are some examples of where this comes up. The definition of the cross product. That's a mathematical thing that comes up in a lot of applications. The orientation of coordinate system axes. Calculation of moment vectors. So when we were doing rotational motion, we did everything in a plane, so we didn't really have to worry about moments being vectors. But in three-dimensional motion, moments are vectors, and coming up with the direction of those vectors involves the right-hand rule. So anyways, this list goes on, but I don't know, it's a useful thing in physics and engineering and math. We are going to use 3 different applications of the right-hand rule. So 3 different applications of the right-hand rule. Like I said, 2 of those will be for calculating magnetic field vectors. One will be for calculating a force vector. We'll get into that later. And here are the 3 applications. The first is calculating the direction of magnetic field lines that are produced by a current through a straight wire. The second, in this application of the right-hand rule, the thumb is going to point in the direction of the current. And the fingers are going to show the circular path of the field lines. Then the second application is going to be the direction of the magnetic field vectors themselves. So notice that in this first one, we were really doing the field lines, and then you have to go from there to figure out what the vector directions are. Here we're talking about magnetic field vectors that are produced by a current through a coil of wire. So the first one was through a straight wire. Now we're doing through a coil of wire. And for this right-hand rule, the thumb and the fingers are switched. So now the thumb is in the direction of the magnetic field vector. And the fingers are in the direction of the current traveling around the coil, because the coil now is a circular path. So the current moving around the coil. Those are the two that are relationships between current and magnetic field. And then the third one is calculating the force okay, let me rewrite this. So the force, a magnetic field applies to a current passing through it. So if a current goes through a magnetic field, the magnetic field applies a force to the current. For this example, the thumb is the direction of the force. And the fingers represent a rotation that aligns the current direction with the magnetic field vector. Okay, so that's sort of a confusing thing, but basically, if you have two vectors, you can rotate one of them to align it with the other one. Okay. If you do that, you're tracing out, say, the tip of the vector that you're rotating makes a part of a circular path. And if you continue that circle, figure out what that circular path is, that's what your fingers do, and your thumb gives you the force direction. Okay, so you can see another reason why this is confusing to people, because there's just there's no consistency about what your thumb stands for, what your fingers stand for. There's just a lot of information you have to get straight here. And so this, making sense out of these three things, is really the main task of this section. Anybody have any questions? Yep.
So if you draw like a bar magnet and show that, because I'm seeing like the loops of the field, and I'm having trouble putting the vectors in a direction with the loops of a magnet.
Yeah. So okay, so if you have a bar magnet, the magnetic field lines, say this is the north and this is the south, the magnetic field lines do something like this, and they actually continue on the inside. And if you want to know the direction of the magnetic field vector at any point on one of these lines, so let's choose this point, then the magnetic field vector is going to be tangent to that field line. We don't know the magnitude, but that's the magnetic field vector at that point.
So then when we see the right hand rule applied, it's just going to pull it towards B. And then the left hand.
Yeah,
Three,
that's right. So if you, for rule 3,
the right hand rule.
okay, so it turns out that applying, so you're right that this does relate to the force that two fixed magnets apply to each other. But using this law to do anything with fixed magnets is really complicated because of the complexity of the magnetic fields.
Okay. You have a different example that's not too complex to apply that.
Yeah. So if you create a magnetic field by putting a current through a coil of wire, okay, so if you send the current this way through the coil of wire, it's going to produce a constant magnetic field down the middle. Okay. And now so this is a magnetic field, we'll call this current 1, and then B1, that's the magnetic field produced by that current. And then we totally separately take another wire and wedge it through here. Okay, and send a current perpendicular to that coil into the page. Call that current 2. Then what you would see is a force applied to this wire I2 by the magnetic field. Okay, wait here a second.